Question number 13, another one from modern physics. So it's basically raining modern physics in this shift, though it's an important chapter we all know. Now here it says, a photoelectric experiment, the wavelength of the light incident is changed from 300 nanometer to 400 nanometer. You need to find the corresponding decrease in stopping potential. Well, if we increase the wavelength, the energy of the photon will fall, and subsequently the potential required to stop the electron would also fall. So that's a reason why increase in wavelength means there is a fall in stopping potential. Now, even for the sake of simplicity in calculation, this thing has been given there. You can go with this way. Hc by lambda 1 is EV1 plus work function can't be written as phi 1, phi 2 because that depends on the nature of metal, which is always same. And in the second case, you get Hc by lambda 2 is EV2 plus of work function. So there are two equations, equation number 1, equation number 2. You subtract them to get the change in stopping potential, and the value will be very, very close to 1 volt. So option number 1 is the correct option for question number 13. Time to move to question number 14 now. Question number 14, another question from heat and thermal expansion here. Let's see. It says that two rods A and B of identical dimension. That means the length, area, volume, everything is same, identical, are at temperature 30 degrees centigrade. So the initial temperature is also same. A is heated up to 180, so the rise would be 150, and B up to T degree. The new lengths are same. So the initial length, they are same, and the final length is also same because it's been given, but the rise in temperature is different, so quite obviously the coefficient of thermal expansion must be different. And here it's given, ratio of coefficient of linear expansion is 4:3. We need to calculate the value of temperature T. So initial length same, final length same. That means the rise in length also has to be same. So for the first one, you get alpha A, L, and the change in temperature 30 to 180, so that's 150. So that's delta L for the first one. For the second one, you get alpha B length, and from 30 to T, so that's T minus 30. So it's so simple a calculation. Now you solve it and you would get 230 degrees centigrade as the value of T. Therefore, option number 2 would be the correct option for question number 14. Time to move to the halfway mark, question number 15. All right, question number 15 from thermodynamics. So you just try to see the analysis. Post-rotation, the chapters are very important. Though many a times we do not tend to give that due focus, but it's very, very essential. So you need to carry that secret point here, all right? So here, a process is there where temperature and volume of 1 mole of an ideal monoatomic gas is varied according to this. K is a constant. And in this process, we need to calculate the amount of heat absorbed by the gas. Well, if I want to calculate that, so what I will do is that first, phi T is constant. That can be written as PV square is constant because T is PV upon NR. So it's basically a polytropic process with polytropic coefficient 2. Now, if I want to calculate the heat, so here what I'll get is, if I want to calculate that thing, that's delta U plus of W. And delta U, the number of mole is 1, CV will be 3R by 2 into delta T, because all of us know that delta U is N CV delta T. And what about the work done? Work done is N R delta T downstairs 1 minus polytropic coefficient. And this now gives us R delta T divided by 2. And that matters option number 2. So option number 2 is the correct option for this question. Time to move for the next one now.